Okay, so we got our, let's take a look at this now. We got the constant for pi, and we created one for sales tax. And one of the reasons for using these constants is for readability. So if I look in this program and I can say, okay, 3.145, we all kind of know that's pi. But it still would be a lot more readable to say that. Something like that, times pi. Oh, we also have to do something called static. Static simply tells the compiler to only create one copy of this variable. And when we get more into object-oriented, I'll explain that later. You see that this main method is static, and I'll explain that a little more later when we get into actual object creation. But there's pi. So that's a little more readable because you know it's pi. And pi is kind of stands out, but what if it's sales tax? And you got something down there like, total equals total plus total times 0.8 or 0.085, right? Or 88.5%. How do you know what the 0.085 is? You could guess it's sales tax. It could also be a commission rate. You have no idea. But if you're using the constant sales tax, then it stands out a lot more. Okay, so here's your numeric data types, and this is a good chart because it tells you what the largest value is, plus or minus. A byte is one single byte of memory. Recall that a byte is made of 8 bits. And does everyone remember that chart that we had from last time? Where I showed you what a byte was? If you've got 1 byte and you turn all the switches on, you get a maximum value of 255. Right? So, for example, if you really want to be conscious of memory, you might store someone's age as a byte. It's highly unlikely they're going to live past 255. I guess they're awfully lucky if they do. And that would be the most efficient data type for storing someone's age, for example. Short is a lot of times called a short int or a small int or a half int. It's essentially 2 bytes or 16 bits. And its maximum value goes to what we would say plus or minus 32,000. Or if I go to my other example here, we'll see that, because I did that down here as well, that it was roughly 64,000. I did that down here, how it works out. Again, starting from 255 and turning the next set of 8 bits on, and doubling it every time, you get up to 64,000, 65,000 and change. Now here they showed us plus or minus 32,000 and change. But your total number of unique values is 65,000, whatever, 500 something and change. An integer, which is what we would call the most efficient data type on an operating system, and that's because it's normally tied to the operating system's memory access capabilities. So, for example, you've probably all heard, about 64-bit Windows and 64, and the Mac's already 64-bit, and most versions of Linux are 64-bit, and the Windows and all those operating systems used to be 32 bits. And the integer usually aligns to whatever that is. And because of that, we would say that an integer is the most efficient data type. Because the CPU is grabbing the equivalent of a int every millisecond or something. And with a short, it's still got to grab that same 32 bits or 64 bits, but it's wasting the rest of it. With an int, it's grabbing exactly what it wants, so it's more efficient. With a long, it takes the CPU 2 milliseconds to get the data instead of 1, because it's got to hit 64 bits, and it can only grab 32-bit at a time. And that's for a 32-bit operating system. For a 64-bit operating system, everything doubles. So it kind of gives you an idea of the way memory works. Remember, memory is made up of bits, or these switches that we turn on and off very quickly. Long is 64-bit automatic, 64-bit, and it is a double, or double the size of an integer. Float, I think they give you an exponential number. It's 32-bit, so it's going to have a plus or minus range of around 32,000, because half of the bits are for the fractional portion of the number, and the other half are for the whole number portion. And a double, which I told you was the safest, it is the highest numeric data type. And it can store a range of... yes, longs and doubles can be used on 32-bit systems. The main difference is the efficiency with which the CPU can grab the data. It's less efficient on 32-bit, but yes, they can do it. You're welcome. So our numeric operators are the addition, minus, the multiplication is the asterisk, the division is the backslash, and what we call the remainder, or the modulus, is the percent sign. So again, these should all be familiar from math. You use the plus and the minus all the time. The backslash is sometimes used for division. Usually you just use the X in math for multiplication. That doesn't really work in computers. It needs to have a sort of special character, so they use the asterisk. And the percent sign would give you the remainder. Divide 20 by 3, the closest you're going to get is 18, with a remainder of 2. So those are your numeric data types. And again, so you got plus, minus, multiplication, division, and modulus. So 5 divided by 2 would yield 2. If it's stored as an integer. 5.0, a floating point divided by 2 would yield a value of 2.5. So what you would get here depends upon where you're storing it and how you're storing it. 5 modulus 2 yields 1, because 2 goes into 5 twice with a remainder of 1. And the percent sign gets you the remainder. So this gives another example here. If we were to take 6 plus 10, which would be 16, divide by 7, 7 would go in evenly twice, 14, and then the remainder would be 2. So that's kind of helpful if you just want to know whether something, what the remainder is. It's also helpful to find out if it's an even or odd number, because an even number divided by 2 has no remainder ever. So you can be useful for that. We're going to look at a time example in a minute. Time can get very, very complicated. Time on computer systems are stored as numbers. It's stored as a number of milliseconds from a base date. So let's say they use a base date of 1900, January 1st, 1900, exactly at midnight. They would calculate the exact time by adding 1 second to that date time, and they store it. And that seems like a lot, and you think about, well, how many seconds are, in a day? 60 times 60 times 24. So what is that? That's a large number. We can calculate it. I think I've got a calc. Calculator. So we said 60 times 60 times 24. 86,000. That's a day. Times 365.25. That's how many milliseconds or seconds you have in a year, which looks like it's about 31 million. 31 million, okay. Times 10. is 315 million, if I'm reading it correctly. 10 years. 100 years would be 3 billion. But we know an integer can store up to 4 billion and change. It's 4 bytes. So even if you stored the number of seconds as an integer, you could still store it as a byte and have over 100 years and still have some time left. Most of what, and actually they store it as a double, I believe. Go back to this. Oh, shoot. Sorry about that. Go up a little bit. Okay, so a long is a very large number. An int is plus or minus 2 billion. Okay, so that's 2 billion, right? What is that? That, I can't even tell you how big that is. Let's see. So that's okay, so we know that this number right here is 2 billion. What is that? It's incredibly larger, isn't it? I mean, so you know that even though, holding every second since a base time generates a very large number, the fact of the matter is a long, for example, a regular integer could hold almost 100 years, and a long can hold quite a bit more than that. So dates and times are stored as a long, and from a base time, really. Some computer systems go back to 1800, January 1st, 1800, and it's still not a problem. Dates and times they have plenty of room, as you can see. This is the maximum value, or excuse me, it's plus or minus that, and it looks like that's, if that's 2 billion, that would be 20 billion, 200 billion, 2 trillion, 20 trillion, 200 trillion. What comes after trillion? I'm not even sure what comes after trillion. So there's more than enough there to even store the national debt several times over. So it's a huge, huge number. Quadrillion is a quadrillion. So that would be what? 2 quadrillion, 20 quadrillion, 200 quadrillion, and we still got another 2 places to go. It's an extremely large number, right? So it's an extremely large number it can store. So, but dates are stored as numeric values. And we'll get a little bit more on this. Displaying time can be very tricky. So we're going to look at how it's done. One of the things you want to do is you do want to avoid floating point numbers as much as possible, particularly when you need a really precise numbers. And it really has to do with rounding errors. And these rounding errors aren't enough to affect any sort of financial calculation. But if you need to see if 2 numbers are equal to each other, they may look like they're equal, but if you're storing them as a floating point, it could be that the 10th precision is different by 1 millionth of a penny, and they will come, and the computer will say they're not equal.